All right, so I'm going to talk about NVMe-over-Fabric support for Ceph. Actually, the whole effort started almost like, I think, 3 years ago now. Um, we were basically asked to see if we can support Ceph with DPU hardware. And we actually tried it out, we ran it, and at least back then, the typical smart NICs that you could buy have very low power ARM cores. So we actually saw very slow performance on the DPUs. And that's why we decided, okay, let's introduce NVMe-over-Fabrics to Ceph. Why introduce it in the first place? I just gave you an example, but you have the RBD2 for remote block storage. It's proven, right? It's reliable object access to sharded and replicated or erasure coded storage in the back, right? So you have all these features, you have fault tolerance and so on. So why do we need to introduce a new one? Well, for one thing is NVMe-over-Fabrics, as just mentioned, is more and more widely used. Everyone is using it. It's kind of the de facto standard to access remote block storage. And if you already have a storage environment where you run NVMe-over-Fabrics, right, it's kind of natural to have other systems, to integrate other systems like Ceph storage systems with NVMe-over-Fabric. And it also makes it easier to switch between those, right, once you have a system like this in place. And as I said before, this was the whole motivation for the work and how we started. You can take advantage of DPUs that have typically NVMe-over-Fabric offloading, which probably you won't see a DPU with Ceph offloading, because that's not an easy task. Okay, so what have we done? We basically looked at what has been done in the past with iSCSI in how to integrate this, and I think we have basically similar design. So this is the overview. So basically you have the Ceph cluster on one side, then it talks RADOS to a Ceph NVMe-over-Fabric gateway, and the gateway is just basically a bunch of processes. I'm going to talk about some details later. And then on the other side, you have NVMe-over-Fabrics in the form of TCP, RDMA, or Fiber Channel. Not sure if anyone is using Fiber Channel, but and then you have the clients on the other side as the initiator, right? And you can run this gateway service. You can run this everywhere. You can run this co-located with your OSDs. You can run it on a standalone machine, right? The thing that you have to keep in mind is with this gateway in between, you're essentially adding a network hop. That's just the way it is, because just how NVMe-over-Fabrics is designed, it's a point-to-point storage protocol, right? So let's see how this looks like. So to give you some NVMe basics, right? So for the rest of the talk, typically what you have an image or a volume in NVMe is a namespace represented by a namespace, which we map to an RBD image, right? And then the RBD image is mapped to object in your Ceph storage. And namespaces are logically grouped into subsystems, and each subsystem typically can have multiple listeners attached to it. And as soon as a client connects to it, it typically creates a controller, or there might be controller already there, but it connects to a controller, and the controller is basically responsible to issuing the actual I/O to executing your operations against the namespace, which we map then to an RBD image. Okay, so what we've done is we introduced this. So I split this here in the view into a data path and a control path. So the control path is actually a little Python process that runs, that exports a gRPC service. And we provide a CLI where you can make like run configuration commands against the control daemon. And the control daemon is basically there to set up the whole mapping, right? So you can tell the control daemon to do stuff like map this RBD image to this subsystem and this namespace ID, create this listener where you want the subsystem to listen at so people can connect to it, things like this, the control daemon is responsible for. Okay, so to basically have the configuration per system, what we do is we store the configuration in a Ceph object actually, and we store the configuration itself in the OMAP of the object. So this the object map is basically key value store that comes with every object in Ceph. That allows us to basically shut down the gateway, bring it back up, and restore the configuration, right? But we use it also for something else, which I'm going to show you in a second. But first, let's talk about the data path. What do we do for the data path? We actually looked a bit in how we want to support this. Initial ideas was to build something ourselves or look for what's out there. You could also use the kernel for this, right? But in the end, we decided to go for SPDK. This is an open source project. It's called Storage Platform Development Kit, I believe. And it's mainly driven by Intel. And it basically, the initial version of SPDK was meant for user-space access to local NVMe storage, but it has been extended to be much more flexible, and now it also supports NVMe-over-Fabrics since a while. And they have this nice abstraction that you can create basically a target and map it to a block device abstraction in the back, and there are multiple implementations, and they already had a RBD block device abstraction. Was very limited, was not very performant, but it worked. So we could actually, when we started this effort, you could actually already set this up and kind of show that kind of the whole thing works. So we expanded on this, and how it works is that our Python control process basically issues RPCs against SPDK to set up this mapping. So you issue RPCs against the control daemon, and the control daemon then sets up SPDK accordingly, right? Okay, so next thing, right? So as I said before, the way how NVMe-over-Fabrics is designed is a point-to-point protocol, right? Doesn't support like a distributed storage system in the back, right? It assumes the path you connect to has all the storage information, like all the data behind it. So if you do I/O against it, all the data is behind that. That means is we don't have erasure coding or anything like this natively supported. So we have to introduce multipathing for fault tolerance or to improve your performance. Obviously, NVMe-over-Fabrics has features for multipathing, which we leverage. So what you basically see here is we have a grouping concept. So a gateway group is essentially multiple gateways that share the same configuration, meaning they export the same subsystems, they export the same namespaces, right, and things like that. So the only thing different is obviously that the listeners on these two have different IPs, and they can also have different ports. So the way we do this is we basically sync on the configuration that we store in Ceph, and we have two ways to do this. The first thing is that we use the watch notify mechanism in Ceph to update each other. And we also have a polling mechanism in the case that one of them crashes while they do watch notify, right, to keep them consistent. And the cool thing is, I think also that you can issue RPCs to any of the gateways in a gateway group, and they will sync with each other to make sure they are in consistent state, right? Through this OMAP in the object. Okay, so now you have set up like multiple paths. We also support stuff like, or we are in the process of implementing this. It's natively supported by SPDK, so it's basically just for us to add the RPCs for it, that you can specify which of the paths are optimized, which are non-optimized. So basically this is as a hint for the client which path it should use to access a particular gateway in this case. Right. Okay. Of course, you can also use the same feature as I mentioned before to do load balancing or scaling. So you can decide, right? And with the asymmetric namespace access, what I showed you before, you can also steer particular clients of a particular subsystem to a gateway and others to other gateways, right? So you are pretty flexible in what you can do there. Okay, so right, so most of these features that I talked about, except ANA, is already available, right? You can download this today and try it out. Fingers crossed it works. You know how it is. So feel free and let us know. Of course, it's all ongoing work, right? We are kind of, we know we need a lot more testing and things like that. So we are still at the beginning, but it's there, it's running. So it's not just me talking about it. Let's talk a bit about performance. So for performance, the goal was, of course, to come as close as possible to a non-gateway performance, right? As if you would access basically directly your RBD image from a host directly to the cluster. Now, as I said before, right, with the gateway, we're introducing basically an additional hop. And even if you co-locate the gateway with an OSD, right, that means that only for that particular OSD you're local, but for all the others, you would still be remote. So it will still be 2 hops. And we have a little, this was run on a little Ceph, on a little lab setup with a 3-node Ceph cluster. And this is on the left side is where we started, on the right is where we are now. So what you see here is that you have, on the y-axis, you have thousands of IOPS. Might be a bit small, but hope you can see it. And on the x-axis, you have volumes, number of volumes, so increasing. And the blue bars are basically native access. We use FIO with librd, so from user space instead of the kernel. And because to make it fair, because SPDK also uses librd, right? And on the right side, we have SPDK with an NVMeoF target and talking to librd on the back. So how this looks like is you have SPDK here, and you have a so we run SPDK with NVMeoF connecting to our gateway, which also runs SPDK, which translates to basically RADOS RBD in the back. And this is how we started. So we were quite far away from our goal in having almost native performance. And this is where we are now. I think it's like, I think we are 8% away from native performance. Obviously, this is kind of small setup, right? It's only 32 volumes. And this was NVMe backed, and it's a 16 kilobyte IO size. It's kind of, you know, quite low in terms of what our 3-node cluster can do in terms of IOPS. That's why we switched in this graph here to a RAM disk-based OSD for our 3-node setup. And we use multiple Ceph client instances in SPDK to improve our performance. And the access now is, again, thousands of IOPS, and then we have numbers of volumes per Ceph client instance, and we run a total of 128 volumes. And having multiple Ceph client instances helps because the Ceph client instances have their own like kind of IO threads and operation threads in librd. So what I will want you to focus on, I know it's a lot of bars, but the one on the red is basically is the best performance in this scenario you can achieve with 8 volumes per Ceph client instance. Again, we have 16 kilobytes, and the total queue depth is 256, and around, I think 16, yeah, these are number of cores, the different bars that you see, and around 16 cores, we actually achieve line speed essentially. So this is a 100 gigabit NIC. If you make the calculation, 16 kilobytes divided by 100 gigabits, it's around 700,000, bit more. Then, okay, there are some protocol overheads, right? So I don't think, yeah, I think I'm pretty comfortable with this number, at least for this setup. Right. And we are currently, just going back to this again, we are currently in the phase of actually testing to bigger scales like 256, 512, and even more, and trying this, of course, to run on a bigger cluster than just our 3-node lab setup. Okay, so let's talk a bit about what we've planned. So our planning is, we have, of course, if you talk NVMe-over-Fabrics, we want the discovery service. And for discovery, there is a native NVMe-over-Fabric discovery, which currently there's technical previews to add centralized discovery, which we want to do. But for now, we're starting with just having a discovery service in the first place, and Intel is helping us here, trying to introduce it. Essentially, what we are planning to do is have this as a standalone service, again, synced via the config, like we have for the gateways. And then these two, in this scenario, they advertise to the clients which path they can use to get to a particular subsystem, right? That's all the discovery service does. So you can basically add gateways, remove gateways, and the discovery service will tell all the clients that are connected to it that there were updates and that there are new paths available, which paths they are supposed to take. The next one is, it's also, of course, a big one, especially if you want to deploy this in an enterprise setting, right? Authentication and encryption support. So this one, what we had in mind for now is that essentially we want to have a plugin architecture where you can add this to the Python daemon, your own authentication or encryption method. And we, as an example, wanted to add this. And essentially what we had in mind is if you have a subsystem, what I said before, each subsystem typically has its own listeners. If you restrict your subsystem to a particular IP port pair and also add some credentials for IPsec to it, right? It basically, if a client connects to it, it's kind of authenticating against the subsystem. Obviously, it's not, because it's IPsec, right? It's against the IP port pair, but it comes as close as possible without implementing NVMe in-band authentication, which we're going to have in the future, or at least we're planning to have. But for now, I don't know at least of a single implementation that implements NVMe in-band authentication. The kernel doesn't have it. SPDK doesn't have it. So this is the state we are at. And I think this we can pretty easily implement without a lot of effort, because, IPsec, all the stuff is already there. We just have to plumb it together. And I think it's already like a usable approach. Okay, so where are we now? As I said before, this is ongoing work. You can try it out today. I showed you the link. So we plan the initial release for Reef. It will be like a scaled down version from what I showed you. So what we plan for now is have a single gateway with the gRPC control, and we will have the CLI, we will have the save and restore configuration, but we will not have yet the multi-gateway stuff. It just needs a bit more testing to refine. And for the future, besides the stuff that I talked about, discovery and so on, we also working on Ceph ADM integration. So I think for iSCSI, it's already there. You can basically say, hey, give me iSCSI gateway on this node, and we want something similar for NVMeoF. And we are working with Intel on something called ADNN. And the idea here is what I said before. Maybe let me go. Sorry for the switching, but I think, yeah, this one. So the idea with ADNN is that the problem is, right, as I said before, if you put a gateway next to an OSD, you always have additional network hops, right? Because obviously your data is typically spread among all these OSDs. And the idea of ADNN is to have a mechanism that they are also trying to get into the NVMe specification, where you run basically the crush algorithm in the target to figure out which of the OS, on the client, not on the target. You run the crush algorithm on the target on the client to figure out which target you need to go to, where basically your data is. That means you need to collocate with each OSD one target, and then you basically do the same thing. But the idea is to make it like lazily update the crash, right? So if you go to a wrong node, you still will be able to do the extra network hop, but in most of the cases you will go to the node where your actual data is. So this is kind of an optimization Intel is working on, and hopefully this will be added to the NVMe spec that makes it more applicable to implementing systems like this. We go back to the last one. All right. Of course, the whole thing wouldn't be possible with tons of people working on this. So this has been a collaborative effort between all those companies listed and all those people listed. I hope I didn't forget anyone. So with this, thank you very much. I hope I see you one of the weekly calls, or download the stuff, try it out, and let us know if it works or what issues you run into. And I'm open for questions. Yeah.
Kind of an easy one. So can you walk me through what the operational maintenance would look like? For example, what changes do you need to make to the gateway if you have an NVMe disk go down, or if you have MTBF hit several disks in a cluster?
Right. So you mean like if you have a disk down in Ceph, or a physical disk? So I mean that would be basically you would deal with this on the Ceph side, right? Since I mean we rely on basically you have the reliability from you have a normal RBD image, right? So it's the same as before in that sense, right? So you need to replace your disk. You need to make sure your objects are redistributed, these kind of things, right? You don't have to reconfigure the gateway, because the gateway just is basically a Ceph client, right? It works like any other client, so it shouldn't notice actually that a disk went down or anything like that. Yeah. The only thing where this might change is if you have something like ADNN, what I talked about, right? And now maybe your backend storage somewhere else that you need to basically update the crush, and then on the client side. But again, this is future things. So
I had a question similar. You might have covered this, but it's a future question probably. Is there thought of, and maybe Josh kind of hit on this, putting NVMe natively in the OSD? Because you're adding a network hop and a translation layer. You're going natively from one protocol to another.
Right.
Is there a thought to try and move to NVMe natively in the OSDs and dual protocol like RBD and NVMe as a performance kind of improvement?
I think, yeah, the problem is, as I said before, is that NVMe, like from the spec perspective, is a point-to-point protocol, right? It doesn't deal with you talking with multiple paths, and the path is actually means one path only has part of the image available, the other path has other part of the paths available, right? In that sense, you cannot natively integrate it, other than you build something like this. You basically extend the NVMe spec to allow these kind of things, right? To have like client-side decision to know where to go to, right? I think that's at least I see the only way forward to kind of make it more native in quote unquote, and to avoid the network hop, right?
Yeah. So is there any advantage to using NVMe over Fabric from a Linux client that already supports KRBD or librd?
I mean, it's more of a if you are in the ecosystem, right? You're already maybe running NVMe-over-Fabrics, at least in my opinion, right? Otherwise, if you're fine with running KRBD, obviously it might give you better performance. You might not have to deal with setting up the whole gateway infrastructure and things like that. So, yeah.
And I wanted to know, like, is it technically possible to run the gateway on the client side? And
oh yeah,
back? Yeah, you can.
You can. You can just run. You can just run this gateway on the client and do loopback to it. That works.
Okay,
yeah.
So then you avoid the hop.
Actually, why you mentioned this, there have been actually some people talking about this for having Kubernetes support, because I think the problem at the moment is with KRBD, you're missing a lot of feature that librd has that haven't been pushed into the kernel. And one way to basically run librd and still have a kernel block device, you could do this, or you do MBD, right? There are a bunch of options, but this was something that was discussed. Yeah.
Hey, so a question for you on the performance side, maybe more efficiency side. So both like target CLI and RBD MBD suffer from a lot of internal memory copies and slow, or actually a high CPU usage due to the internals. And I was wondering if you guys have had to deal with much of that as you've been developing this.
Yeah, so I mean, I don't want to lie. The gateway obviously is heavy in terms of number of CPU cycles you need to push stuff around. I mean, if you want to run the whole Ceph protocol and the NVMeoF target and want to push 100 gigabits, right? You need some cores, and you also need memory, right? So as you've seen before, I think this one, so this one achieved line speed with 16 cores basically running at full blast in SPDK. I'm not saying that this is the final thing. There might be some improvements to it, but you need to spend some of the performance. And we looked into memory consumption, so there might be some ways to improve that in SPDK. And one other thing is also per default, SPDK is just polling all the time on all cores. You can turn this off. They have a new feature where you can basically say it goes into interrupt mode, quote unquote. But yeah, these are definitely concerns that we are looking into and trying to optimize this as much as possible to keep it down.
Yeah, let's talk more later.
Sure, yeah.
I was going to comment on Dan's question about if you have an RBD client, would there be any reason to use NVMe? And I would say one potential benefit is on the client side, it could potentially be less CPU that's consumed. I mean, it's really moving it to the target, right? But you could also have a hardware NVMe initiator, and then the CPU consumption on the client side would be much lower.
Yeah, that's actually a good point. I mean, the NVMe client-side protocol is actually pretty slim, so it's much more efficient than running the full-blown librd or KRBD. But obviously, it needs to be. It's clear, right, from what I said before. One is point-to-point, the other one does the whole thing with figuring out where to go, all these kind of things, right? Sure, yeah. I think there's one more here.
Doesn't anyone but want to put a native RBD client into a NIC, into a smart NIC?
Yeah, so we talked to Xilinx. They have one, but I think they are still a long way out to having actually something that's performant and that you can run on 100 gigabit, at least from what I've heard.
Some other things. It looks like you got a lot of the performance through concurrency, just adding more and more volumes. Were there other tunings that you've done to get the performance up to that 92% roughly
Right. So that was mostly stuff we did within SPDK. So there were some issues with IO. Like as I said before, they had this RBD block device, but it was kind of just a showcase thing. It was not actually used. And for instance, all the IO was funded through a single core. So we had to fix that. Then there was a lot of like how affinity of libRBD thread was handled in SPDK. We kind of fixed that. What we now have is that actually when you create a client instance, you can tell it which cores the libRBD threads should be running on. And before it was like, in the very first version, it would run on the same cores that the target would be running, which is obviously pretty bad. And now we have this option that you can actually move them out. So these kind of improvements, there were a few more that help to get basically to this 8% off for what we are at the moment. Yeah. Yes. Yeah. We do. All right. Seems like that's all the questions. Thank you, everyone.